This notebook is made for medical professionals with very limited coding ability who want to contribute to creating AI algorithms related to chest x-rays. If you've worked in a hospital, you probably already know there are a lot of chest x-rays and relatively few people with very little time on their hands to read them. In theory, AI could help these people, but in order to create functional, correct, and helpful AI, we have to feed the algorithms we create very good data sets. These data sets, if we're talking about creating an algorithm based on machine learning with chest x-rays, would have to have images that are proper and properly labeled. So we have a bit of a problem. If our hardworking radiology professionals already don't have time to read all the existing x-rays, how will they have time to read more to create an algorithm? It's almost like in chemistry, when if you could get past a certain energy of activation, you could change the whole system, but the system doesn't necessarily push it that way. cleanX can help. So what I'm going to show here is a notebook. A Jupyter notebook is a tool which allows us to interactively run code. I've written cleanX in Python because it's a very popular language. And I've made functions that make it very easy to contribute to making a machine learning data set, which will power any kind of machine learning product. So here I've imported pandas, a few other libraries, and of course from cleanX, the modules dataset processing, DICOM processing, and image work. Here I'll focus just on some of the functionality in image work, which would ease contributing to making a quality machine learning product. I read in a bunch of images that were put together by Mr. Praveen Govindaraj. He made a data set of chest x-rays called the Corona Hack Chest X-ray Dataset for Kaggle. Mr. Praveen is not a medical professional, so we should not expect this data set to exactly reflect the kind of data set we would put together if we were making data set for machine learning. In any data set, we might want to take a look at the duplicates. So we can do that in cleanX very quickly. And it turns out in this data set, cleanX finds 26 duplicated images, which is not a lot in over 5,000 pictures. It's actually under 1%. And we can just look at the amount of academic curiosity. And when I did that, I see that actually we had triplicates. So the function show images of DF is only going to show the duplicated ones. So we had some that were duplicated twice, it looks like. Now, out of all these images, this isn't that many duplicates, but when you have 3, 4, or 5 of the same image, if someone looks back on your work and sees you didn't pull them, they might claim that you were lazy. So you probably would want to pull those out. We can also look for outlier images. Now, I've worked with a lot of different chest x-ray data sets, and sometimes you'll find images that are inverted. Sometimes you'll find images that are upside down. Sometimes you might find images with text on them that labels them. You'd want to pull all of those out. I'm not going to do every function that cleanX allows, but I'll just show a few functions that aren't that intuitive. I think the functions that help you find text written on the image are pretty intuitive. Obviously, if you're doing a machine learning project to diagnose COVID or pneumonia, and the chest x-ray has written in on it COVID or pneumonia, you would want to pull that, and that's obvious. But there are other kinds of images you would also want to find. Maybe there are some fluoroscopy images that stuck in. Maybe there are ones that are turned upside down, and you would want to think about pulling this as well. So In a chest X-ray, we would expect usually the upper part of the image to be on average darker than the lower part because most people's neck is smaller than their abdomen. Um, so we can check about that in a couple ways. We can check just the average of the upper part with the function find by sample upper, and say we want to look at, say, the upper 10% and compare it to a certain number, 200, or we can compare the upper and the lower. The third function I'm showing here, find tiny image differences, takes all of the images in my data set and makes a sort of average image, and then looks at each image and says, how different is it? And then I can take out a certain percentile that are very different. So let's get going with that. Let's look at a function that compares the upper and lower part and its results. There's a lot of results here. I don't want to look at each of them. But on the other hand, it's 322 results. It's a lot faster than looking at 5,000 something pictures, okay? But let's see what our other checks turn up, because I can already see in this, I've got some axial CTs, but I've also got some images where maybe the patient just had their arms up, some pediatric images. I'll come back to that. Okay, so now let's just look at the upper pixels and see, and take this approach to finding outlying images, okay? And it turns out this pulls up a bunch of CT images. If we're making a data set of X-rays, we don't want CTs, and certainly not axial CTs, right? And it also pulls up some pediatric images that are maybe their fluoroscopy, because they're just they're not on the same range of pixel data values. We'll have to look at them more closely, but probably none of these images, belong in our final data set, which we want to be a quality data set of just adult COVID-19 X-rays, unless, of course, we're making pediatric data set. So let's compare, using our find tiny image differences, each image to a sort of average image, and look at the 1% that really outlie. And if we do that, we get back, surprise, surprise, a bunch of axial CTs, as well as some sort of different images. Now, some of these images are fine, but the point is that instead of looking at 5,000 images, we can now look at the 1% that most outlie by certain parameters and quickly pull them out. So in a matter of minutes, while sipping coffee, we can clean up our data set a lot. We don't have to look through all 5,000 images to get the true outliers, which maybe are images that never should have been in such a data set if we want to create a quality machine learning project. cleanX has many other functions, including ones that allow you to find images with text, and ones that allow you to compare images in different ways. But this notebook is just an example of how you can use some very simple functions in cleanX while you take a coffee break to try and find images that you would want to pull out of a data set. Remember, the higher quality data set you can give programmers, the better an algorithm they can create. So you will not have to use many lines of code. You can simply use the code in cleanX, and feel free to copy some functions or use the functions directly from the library to create a notebook or code. And you should be able to spend much less time creating a much higher quality data set.